Greetings and welcome to the Dr. J vlog series. It is Monday, May 5th, 2025. Happy birthday to one of my big sisters, Patricia. Trish is, well, I won't say her age. She's a little bit older than I am, though. I'm the youngest of six. But happy birthday, Trish. And today, on Mondays, that is, we talk about mathematics and statistics. So mathematics, in my view, it's the ultimate sort of stand-in or representation of the patterns in nature. They're found everywhere, throughout nature, throughout the universe. And mathematics, remarkably, represents these patterns. We can describe basically anything that we can see or even imagine through some type of mathematical terms. So, just quite commonly, we describe our height and our weight, of course, using mathematics. And we use numbers all the time to describe the quantity or the amount of something. Think of the math involved simply in cooking or following recipes, all of which reflect underlying patterns that are involved to generate certain kinds of food, certain kinds of outcomes, if you will. There's math involved in designing everything that we create, whether we're explicit or even aware of what we are doing formally. And we use the math all the time to describe the patterns that we find in nature, from the temperatures that we experience to the length of the sound waves that we hear, from the acceleration of objects due to gravity to the speed of light, from the number of stars in our galaxy to the distance spanning the visible universe, or at the very edges of our universe. So currently, by the way, how old is our universe? Well, we don't know exactly, but we estimate that it's about 13.8 billion years old. By the way, can we know that with certainty? I don't think so. It's our best current guess. And that's based on our understanding of the cosmic microwave background radiation. It was discovered in the mid-1960s, or confirmed as such. And it's also based on certain cosmological assumptions or parameters. So as we continue to study these details and new evidence emerges, for example, from the James Webb Telescope, the estimates with respect to the age of the universe are almost certainly going to be revised sometime within the next decade or two. Now, all that said, there's one thing that's always fascinated me about numbers. Well, actually many things, but in particular today, it's the distinction between rational and irrational numbers. Okay? So what am I talking about here? Let me just change up the view here. All right, so rational and irrational numbers. I suspect many of you probably understand the distinction quite well, but just as a brief reminder, okay? Rational numbers are those that can be expressed as a fraction. That is a ratio of two integers. And so any ratio of two integers we describe as fractions. And all fractions then are rational numbers, such as 3/4, 3/4, or -10 divided by 3. Those are fractions. Positive, negative, doesn't matter. They're rational numbers. Furthermore, finite decimals that come to an end are all rational numbers. I give the example there, 0.688. That can be expressed as a fraction. 688 divided by 1,000. Or 3.53. That can be expressed, again, as a fraction. 353 divided by 100. And there are other ways to express these fractions too, but the point is that they all have a finite set of decimal places. They come to an end. And that includes even those that have repeating patterns. So for example, if you have a decimal with a repeating pattern like 0.171717 to infinity, then that's a rational number too. Why? Because that actually can be expressed as a ratio or a fraction of 17 divided by 99. or 17/99, if you will. Okay, the bottom line then is that there are patterns here. And anywhere you can express something as a ratio of integers yields a rational number. And we use these all the time in our daily lives. But what happens if we can't do that? That is, what if we can't express the number that we're describing as a fraction? Well, that's when we get irrational numbers. So irrational numbers, by definition, cannot be expressed as fractions. So what do we know about them? Well, for example, what about the square root of 5, just as a simple, straightforward case? We know that the square root of 4 is 2, and we know that the square root of 9 is 3. And so 5 lies somewhere in between 4 and 9, obviously, which means that the square root of 5 must be greater than 2 and yet less than 3. And so if you use a calculator, you'll quickly find that the square root of 5 is equal to 2.2360679775 ... In other words, that is, I've only provided the first 10 digits, but the decimals go on endlessly. That's what the ... represents, and crucially, without repeating. Never ends. So as such, you cannot express the square root of 5 as a ratio of two integers, and that makes it an irrational number. Famously, think of the expression pi. We're all familiar with pi. It's an irrational number. Most people learn that pi equals 3.14, but of course it's actually much more than that. And again, I've given the first 10 digits, 3.141599265, and it goes on again forever and without repeating. And so irrational numbers then are simply those that cannot be expressed as a fraction or a ratio between two integers. And so the numbers go on forever without any discernible repeating pattern. Most numbers that we interact with on a daily basis are rational, kind of like people in general. Yet there are some oddball numbers out there that exist that we encounter, and they're by definition the irrational numbers. Again, kind of like some people you might know. And that again includes the famous figure pi. So in truth, though, there are actually far more irrational numbers than there are rational numbers. Why? Well, for example, there's at least one irrational number between any two rational numbers. So that's a guarantee. And also, every time that you add or multiply a rational number by an irrational, you're going to get an irrational number. It's mathematically provable as such. And the point is that just on a day-to-day basis, though, we really don't work with irrational numbers too often, or they're not central to our everyday concerns, maybe unless we're a mathematician or a physicist who uses the term pi, an irrational number. So, for example, we'll eat 2 or 3 eggs for breakfast, maybe even 3.5 eggs, 3.5 eggs, but we never think to ourselves, you know, this morning I think I'm going to eat pi number of eggs, 3.14 eggs. It'd be silly. So trust me, there's an infinite number of irrational numbers that are lurking out there. If we wanted to look for them, if we wanted to uncover the underlying order that exists within nature. And so these irrational numbers seem to have no finite end or fixed pattern, and yet they're absolutely essential in terms of describing key facets of nature. They help provide the final glue that orders all of nature and holds it together. It's actually quite remarkable, in my view. So the irrational numbers then help solve the order problems of nature just as much as the rational numbers. So again, consider pi. What's pi? Well, it's the ratio of the circumference of a circle to its diameter. You probably all learned that in grade school at some point. British mathematician William Jones devised the symbol pi back in 1706 to represent this well-known, this famous ratio. And it was later popularized by the well-known Swiss mathematician Leonhard Euler, E-U-L-E-R. And so while pi solves real-world geometric problems, we use the approximation of 3.14, or sometimes the fraction 22 divided by 7, 22 over 7, for our everyday calculations. If you're interested, of course, you could go much further. And so I've just presented there on the screen pi to 39 decimal places, if you want to be more precise in your calculations. But if you really want to be precise, by the way, you might be pleased to know that a U.S. computer storage company last year has calculated pi to a world record 105 trillion digits. Remarkable. The calculations took 75 days to complete and used up to 1 million gigabytes of data. But anyway, I don't know about you, but I personally can sleep better at night knowing that finally we've gotten pi up to over 100 trillion digits, Whew. Anyway, and then, the point is that pi then shows up in all sorts of mathematical equations, but especially in Euclidean geometry. Most of you know not only that pi, the definition of pi, or the calculation of pi, the basic calculation, but you probably also know, for example, the area of a circle is given by what? 2 pi r, by pi r squared, right? Pi r squared. So I was just going to talk about the circumference, but that's okay. These are all sort of commonly known mathematical expressions using pi. What you may not know is that pi also shows up in a number of standard physics equations. And these, again, have been devised, discovered to describe all kinds of different facets of the universe. So I've just provided 3 kind of famous examples, if you will. Not that you necessarily know these equations. You don't work in physics. You almost certainly don't. But there's the cosmological constant, which again, pi there ends up in the numerator. You have Heisenberg's uncertainty principle. And again, if you don't know anything else about Heisenberg, maybe you watched Breaking Bad, and there's a specific reason that they chose the name Heisenberg. Look that up if you don't understand. So yeah, that shows up in the Heisenberg uncertainty principle, that equation. And then it shows up in Einstein's incredibly, groundbreaking, famous field equation of general relativity. So again, these are just merely a few examples, and there are countless additional equations in physics and beyond. And so we might ask the question, well, why does pi show up in so many places? Well, because we live in a complex but geometric universe that involves circles and ellipses and spheres and all kinds of circular patterns and motions. Indeed, pi helps to describe sound waves and electromagnetic waves as well. And pi shows up in our probability functions and the normal curve distribution. Somebody like me who works with statistics a lot, this is a common feature of what we do. And perhaps most remarkably of all, if you didn't know this, pi shows up in a number of biological processes, such as the formation of stripes on a zebra or spots on a leopard. In fact, the field of biophysics has revealed that pi appears to be intimately woven into periodic processes that emerge in nature. It appears in the governing biophysical laws of cell division, or the timing thereof, also with respect to heartbeats, breathing cycles, and circadian rhythms that control sleep-wake cycles. But these are topics for another day. I just find it remarkable that pi should show up in so many places in the natural universe. So today, let's just appreciate that we need both rational and irrational numbers to help us understand and explain all the properties of the universe, from the physical to indeed the biological to statistical distributions. And I, for one, am eternally grateful for both kinds of numbers, and even more grateful that we've had these brilliant human beings over the centuries who've helped us to understand not only the nature of irrational numbers, but how they help us to solve the mysteries of the universe and even much of our everyday lives, even though, as I said, we're probably not aware of just how often we come across these numbers. All right, that's it for today. Until next time, may you and yours continue to create peace in your lives, nurture love in your hearts, and dole out hugs in abundance. Take care.